Last class, we start to introduce the wave. Wave is the propagation of disturbance or oscillation. It's the propagation of the oscillation. Okay. So, if you can initiate some oscillation, like here, then this up and down oscillation will be propagated to this direction. Okay. At any point along the wave, the real material or the medium, see, it's in oscillation at the origin, its own position. This object, this real material itself, doesn't move to the direction of the wave, right? Here, the wave is in this direction. So what it actually goes to that way is this shape of peak. You see, the peak goes to that way. So the key point is that it's only this kind of patterns is moving along the direction of the wave. Okay, not the real material. At the same time, since the pattern of the motion is propagating, it will carry energy and the momentum. Okay. So wave can carry energy and momentum. In fact, in the universe, most of the energy is stored and carried by waves. Okay. So sometimes we can refer to the wave as pure energy, okay, without mass. Now, let's look at the types of wave. You can make classification of waves in terms of different criteria. Okay. First, if we, in terms of the medium to support the wave propagation, we have the so-called mechanical wave and the electromagnetic wave. Okay. Mechanical wave are those common waves we see in our daily life, like the sound wave, water wave, waves on the string. These are called mechanical wave. They call mechanical wave because there's some mechanism between the medium, so that makes the wave propagate through the medium. So mechanical wave has to be propagated through some medium or through some real material. For example, for the sound wave, it can propagate through solid, liquid, and gas. Okay? Usually we hear sound because air can propagate the sound wave. In the vacuum, you are not going to hear any sound because sound wave cannot propagate it through the vacuum. Okay. Similarly, water wave propagates through water. Waves on the string propagate through string. Okay. Electromagnetic wave, that's a broad spectrum of all many kinds of waves, like the light. Light is actually some kind of wave. Light wave, microwave, okay. Even sometimes we call say those gamma rays. These things, they are electromagnetic wave. Okay. They are different with mechanical wave. Basically, on the fact that they can propagate through vacuum. Okay, mechanical wave cannot. But all electromagnetic wave can propagate through vacuum. Okay? So like we receive the light from the sun, but between the sun and the earth is vacuum. Okay, so electromagnetic wave can propagate through the vacuum. In fact, from the modern point of view, we're not going to say it's propagated through the vacuum. In fact, we would say it's propagated through the field, electromagnetic field. Field is some kind of material but it's not the real material we are talking about. It's not composed of atoms of the molecules. It just seems empty space. But in the empty space, there are something there. Okay. We call it electromagnetic field. And the electromagnetic field can vibrate to form the electromagnetic wave. Okay? Field is something, some material doesn't have any mass. So it just looks like a vacuum. In that sense, there is no real vacuum. Okay. Anywhere, even in the outer space, even there is no any atoms, molecules, you still have the field. Okay, electromagnetic field, gravitational field, all these things. So precisely speaking, in modern physics, when we say vacuum, we don't think that this is some empty space. Vacuum is something filled with all kinds of field. Okay. So this is the electromagnetic wave. In terms of the medium, what can sustain the propagation of the wave? The real material or field? Okay. Or electromagnetic field. Now, in terms of the disturbance pattern, you can have the so-called transverse wave and the longitudinal wave. Okay. Transverse wave means the wave, for the wave, the direction of the oscillation is perpendicular to the direction of the wave. So if wave goes to this direction, then the oscillation is along this direction. Longitudinal wave is something like if this is the wave propagation direction and the oscillation is also in this direction. Okay, longitudinal transverse. And we can have this to show. We have transverse wave and longitudinal. Okay. We can show like this. Okay, transverse wave is something like this. So wave is propagated through this direction, right? Back and forth. And the oscillation, if you look at each bar here, each point here, the oscillation is up and down this direction. So they are perpendicular to each other. That's called transverse. Now, if I try to make wave like this, it's a little bit difficult. You probably cannot see it very well, but if I propagate wave like this one, okay. You see, still the pattern goes to this way. But in each part here, now it's oscillating like this way, in the same direction. This is called the longitudinal wave. In terms of the common waves we ever seen in our life, sound wave is longitudinal wave. Okay, sound wave is so it's kind of the compressing and extension of the air. Okay, in the same direction. So if I speak to you, I kind of disturb the air near my mouth, so this kind of oscillation pattern is propagated to you, so you can hear the sound. And water wave, what kind of wave it is? Transverse or longitudinal? Transverse, right? Surface water wave, you can see it. The water oscillates like this way and is propagated horizontally, something like this. Okay, this is a transverse wave. And waves on the string, transverse or longitudinal? Transverse, right? Okay, if you have a string, so this is different. If you make some wave like this, you can see the wave is propagated from this direction to that direction, but its oscillation is like this. Okay. And by the way, if I only make one oscillation like that, the propagation is also a wave, but it's a pulse. Just one peak goes that direction. But usually when we talk of wave, we will keep making one peak after another peak. Okay. So that's the transverse wave and the longitudinal wave. And electromagnetic wave, please note that they are all transverse wave. The direction of the oscillation is perpendicular to the direction of the wave propagation. Okay? So that's the difference between the transverse wave and longitudinal wave. Either perpendicular, transverse means being perpendicular, longitudinal means parallel. Okay? So that's in terms of disturbance pattern. Perpendicular or parallel. And in terms of traveling or not, we have the traveling wave and the standing wave. As indicated by the name, traveling wave means the wave is propagating to some direction. Okay. Standing wave, it says that the wave is not actually propagated. Okay. We're all familiar with the traveling wave, like this, right? But what is standing wave? Okay, so this is standing wave. So traveling wave, can see the peak moves from this side to this side. But you can see for the standing wave, the peak is always at the same position. It stays there. This is also wave. Nothing is propagated. It's still called wave, but it's called a standing wave. Okay? And here, in fact, we can also make the standing wave. Usually, I need to, okay, if I just give it this way, one wave, so it will be the standing wave. But now, let me do this. I will make some forced oscillation. Okay? Okay, so for some appropriate frequency, it's the DVD code. Okay, like this. Can you see every point is just oscillate at the original position. The peak is not moving to the left or right. Okay, and if you can see when I try to make the standing wave, you need to adjust your frequency of the oscillation, the source oscillation. Okay. So, what's special about the standing wave is that for any specific apparatus here, to make standing wave, you cannot make standing wave for arbitrary frequency. It has to be some particular frequency. Okay. So you need to find this particular frequency and then oscillate it with that particular frequency. Then you can make the standing wave. And traveling wave you can make for any arbitrary frequency. Okay. 1 Hz, 2 Hz, 3 Hz, 1.5, 1.6, 1.7. But the standing wave, it can happen only for some specific frequency. And these particular frequency are actually related to the natural frequency of the system. usually they will be multiple of the natural frequency. Okay, so for some object, for some system, is the natural frequency omega equals to, let's say, 200 hertz. That means 200 hertz. Hertz is unit of the frequency. 200 hertz means 200 cycles per second. Okay. Then to make the standing wave, it has to be either 200, 400, 600, 800, like this. So that is 1 times omega. This is 2 times omega. This is 3 times omega. This is 4 times omega. Okay. Here you can only make this particular frequency to sustain standing wave. But for traveling wave, it doesn't matter. You can even travel wave with 1, 2, 3.4, whatever number you want. Okay. And what makes wave stand? Okay. In fact, the standing wave comes from the fact that for a system, when I make the wave, it first goes to that direction, but at the other end, it will be reflected, go to the opposite direction. Okay. So at the same time, if I keep making the wave, that's what we call the incident wave to this direction, and we will keep having reflected wave in this direction. The wave moving in the opposite direction, they can be added together. Okay, sometimes they can be added together to form the standing wave if the frequency is incorporated like this. Okay. So one wave goes to this direction, another wave goes to this direction. So their propagation is cancelled. Okay, so to form the standing wave. Traveling, okay, we say the wave propagates energy and momentum. Traveling wave doesn't. Oh, standing wave doesn't. Okay, so in fact, precisely speaking, when we say wave carries energy and momentum, we refer to the traveling wave. Standing wave can store the energy into it, but there is no energy and momentum propagation. Okay. So that's the traveling wave and the standing wave. In the quantum mechanics, we have some kind of idea like this. Every matter, every material, okay, they are actually some wave. Okay, we are the wave. Our body is a wave. Matter, we call it matter wave. Atoms are waves. Electrons are waves. But here, when the system, like if our body in a standing wave form, okay, if we take a form of standing wave, then our energy is not lost. It's not lost, okay? There is no loss or gain of the energy. So we are in a stationary state. Okay. But if the energy can change for the object, okay, like with some object in acceleration, then the object will take the form of traveling wave. Okay, so there is energy propagation. So our existence in terms of traveling wave and standing wave. Standing wave takes a very important form, important role in the establishment of the quantum mechanics. In fact, what we mean by quantum mechanics, originally it means that energy is not continuous for all the objects or the electron atoms. So that we have the energy quantum. And in terms of the standing wave, this is understand that you can only make standing wave for some particular frequency, right? Like here, 200, 400, 600, 800. So the energy is related to the frequency for the quantum mechanics. So the energy can only be some particular value, and we call them energy level. Okay, it's not continuous. You cannot have any arbitrary energy for the object. Okay. Now,